This meeting is being recorded.
Assalamu alaikum wa rahmatullah. We are group number 10 and we are going to represent our OS project, which is visualization of the primitive sequential algorithm. My name is Loy Rafat Al-Qadasi and the second member is Khalid and third member is Laith Amjad. This is our table of content. We'll start by introduction, OS concept explanation, real-world scenarios, and the project workflow and tool demo. Then we're gonna end up with the reflection and results, and lastly, the conclusion. So for the introduction, first, the project goal. To visualize the primitive scheduling algorithm, specifically shortest remaining time, the SRT, and round robin, the RR, using the Python and Python tkinter for the simulation tool in order to show our project by using the VS Code. So the team introduction as well, I introduced my team members like my name is Loy Qadasi, then Khalid, then Laith. We are contribute to different aspects of the project. Presentation outline. The outline of the presentation is explaining the OS concept, demonstrating the tool, presenting real-world scenarios, and discussing the results and reflections. And here we go with the challenges of the static learning. The static example can be confusing. ها؟ في واحد منكم يتكلم يا شباب ولا لا؟ في أصوات تطلع. أوكي خلاص نواصل يا شباب.
كومبليت لوري.
Okay. The challenges of static learning. The static examples can be confusing. Dynamic interactive visualization, enhancing understanding of SRT and RR algorithms. The tool benefits that the students can test cases, visualize context switches, and can see the performance of metrics for deeper insights. Lastly, improved comprehension. Interactive tools clarify the deepen understanding of the overcoming limitations of textbook learning. That's my part, and then we will go into the OS concept explanation with the Khalid.
Assalamu alaikum. So I will continue with the OS concept explanation. So visualizing scheduling is crucial because it makes abstract concepts more tangible. Static text box example can be limiting, while dynamic visualizations enhance comprehensions. Our tool lets the students interact with the algorithm, visualize context switches, and view real-time performance metrics. So primitive scheduling allows the CPU to interrupt a running process if a higher priority arrives. The improved system responsiveness and ensures fairness, especially in multi-user environments. Actually, in this project, we implemented two algorithms: shortest remaining time and round robin. Both are widely used primitive scheduling techniques, and we will explain each in detail. What's the next? So SRT selects the process with the shortest remaining burst time. It's designed to minimize the average waiting time and is particularly efficient in batch processing scenarios where a short job can be completed quickly. So this is about the shortest remaining time. Go to the next round robin. All right, so round robin assigns a fixed time quantum to each process and cycle through them. It emphasizes fairness by ensuring all processes get CPU time. The time quantum is key. Uh, Actually, it affects performance and context switching frequency. So yeah, that's it for the round robin. Go to the next to the real world scenario with Layth.
Assalamu alaikum. I will start explaining for real world scenario. So can you move to another slide? Okay. I will start by explaining time sharing systems. These systems allow multiple users to access computing resources at the same time by rapidly switching between processes. First, we have cloud servers, where many users' processes run at once, ensuring that the system stays responsive. Second, resource management is handled using primitive scheduling, which helps divide CPU time fairly among users. Finally, user experience remains smooth and responsive even when many people are using the server at once. So I'll move to another slide. So now we have the operating system. Let's take a look at how operating systems use similar time sharing techniques. In a multitasking environment, the OS fairly gives CPU time to many applications using primitive scheduling. This improves responsiveness, making apps react faster to users. And lastly, application fairness ensures no signal program uses all the resources. Every app gets a fair share. In short, time sharing and primitive scheduling help keep systems fast, fair, and user-friendly. So we are gonna to go with another slide. There's no sound.
All right, here we have the project overflow and the tool demonstration. All right, the input fields are allowing users to input arrival times and the burst time, as well as the time quantum in case of the round robin, only the case of round robin, and algorithm selection. So the simulation the start simulation triggers the visualization displaying the live Gantt chart as well. So we use the Python tkinter to that tool developed using Python tkinter for the graphic user interface that ensuring user-friendly design. And now we are going to the code itself to run it. Okay. Can you see my screen?
Yes, yes.
All right, and here we are going to run the code. As you can see here, the user input here, it's the arrival time at first. You add the arrival time. We had slides to show the RR input and the Gantt chart explanation for the CPU fair sharing. And this is the fields. This is our RI input. It's 0 to 4, and the burst time going to be 8, 4, 2, and 1. The quantum is going to be 2. So 0 to 4, 6. This one is comma separated, 0 0.2.4.6. And also the burst time is going to be 8, 4, 8, then 4, then 2, then 1. Since we are selecting RR, we need to add the quantum, which is 2. So when you run this code, start simulation, it shows you everything you need. This is the Gantt chart. And this is the average waiting time is 3 seconds, and average turnaround time, which is 6.75, and the contest switches, which is 6. We can test the other one with same input, but we have to test the shortest remaining time. Start simulation. It's almost the same. The time it's different now, 2.50, 2.5. The turnaround time, the TT is 6.25, and the context switches is 4. This is our code demonstration. We use the Visual Studio as our tool, and we select the Python language for the simulation, and that's for the demonstration. Okay, let me just go to the slide again. Okay. This is the test. We already tested right now. And this for the first CPU sharing, as Khalid and Laith stated back then. So the result and reflection.
Okay, so now let's take a look at the peer feedback we received on our simulation tool. The response highlighted three key benefits. First, there was a clear understanding improvement. Many students mentioned that the tool helped them quickly grasp the difference between shortest remaining time (SRT) and round-robin (RR) scheduling. Second, it contributed to enhanced learning, confirming the tool's value in making the content more engaging and easier to understand. Finally, it improved learning efficiency. Students reported that using the simulation made the learning process faster and more easy. So let's move to the slide. So now we have the adjusting test cases. We have three key adjusting test cases. First of all, we have test cases. Students can adjust test cases to evaluate context switching and show performance matrices. Number two, we have performance matrices. Students can see performance matrices to deepen their understanding. Third, we have the evaluation. Students can see and evaluate the overall performance and scheduling. So last but not least, we have another slide. I think it's conclusion. Support for
All right.
support for Khalid.
Thank you all for your contribute in the presentation. So actually, in summary, our tool successfully implements primitive scheduling with the shortest remaining time and round robin. It offer a practical, interactive way to enhance learning in operating system courses. So actually, in the future, we plan to add more scheduling algorithms. Introduce more details, metrics, so and enhance the user interface for an even better learning experience. So in the last week, that's concludes our presentation, and we really thank you for your attention, and we thanks all the members that contribute in the presentation.
Thank you very much, Mr.
Thank you.
Khalid and Mr. Laith. Really appreciate your work and happy to work with you.
Thank you
Thank
so
you
much.
so much.
Right.